this one. A flat coil of wire carrying a 10 amp as shown above. Sorry. A flat coil of wire carrying a current of 10 amps as shown above produces a magnetic field of 5 times 10 to the negative third Teslas near its center. Additional loops of the same diameter are added to increase the number of loops in the coil from 4 to 16, and the current is kept the same. The magnetic field at the same point due to the new coil is most nearly well. So one thing, we do not directly have the equation for magnetic field around a loop of a wire. The College Board doesn't give it to us. They don't express that we need to know it, but they did tell us that the magnetic field around a current carrying wire is just mu naught I over 2 pi r. So they did tell us, hey, the magnetic field around a wire, right, created by a wire, is directly proportional to the current. So we kind of have to make a logical leap here. We kind of have to make a step and say, well, we first have 4 loops. So we kind of have like 4 times, right? If we have 10 amps going throughout this wire, we kind of have like 4, let me draw here, 4 little pieces of wire that are carrying 10 amps. So we kind of have like, I don't know, 40 amps that are creating a magnetic field. And then what they want us to do is kind of make that leap, make that step that says, okay, if we now have 4 of these, 2, 3, 4, I don't need to draw it. You guys know what 4 looks like. If not, that's something to do during this break, is figure out what 4 is. We have 4 times the amount of wires. So we have 4 times the amount of loops. We can make a reasonable guess that we will have 4 times the magnetic field. So this times 4, which is a number that I should totally know. What is it? 20 times 10 to the negative third. Is that how numbers work? So that's 2 times 10 to the negative second is the same as 5. Yeah, that's how numbers work. All right, cool. Dope. Dope, 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 dope.